Hello, this is session 2. In this session, we shall have an introduction to complex numbers. In the previous session, I have explained about mathematical analysis and its sub-branch complex analysis. As I explained, mathematical analysis Mathematical analysis is a branch of mathematics which deals with the study of limits and its related theories such as differentiation, integration and so on. So you have studied this mathematical analysis since PUC under the title calculus. So calculus deals with the elementary concepts of mathematical analysis. I can say it is the elementary level of mathematical analysis. And also, as I explained in the previous session, mathematical analysis has 6 sub-branches, namely real analysis, complex analysis, functional analysis, differential equations, measure theory, and numerical analysis. And among that, this time we shall deal with complex analysis in detail. So in this complex analysis, we came to know what we mean by analysis. Now we shall see what we mean by complex analysis, right? Now, before going to the word complex, now I want to recall the number system. The number systems. So, if I say mathematics, the first thing which will come to our mind is numbers, right? So, number systems start from the natural numbers. The set of all natural numbers. Set of all natural numbers. Which is denoted by script n. Is denoted by script n, and this set of all natural numbers consists of the counting numbers 1, 2, 3 and so on. And we also know that they are countable in number. Right? This is the first number system. Then we extend this number system, the natural number system, to the whole number system, which consists of those counting numbers, those numbers 1, 2, 3, along with the null value 0. So 0, 1, 2, 3 and so on. So this set of numbers constitute the whole number system. In ancient days, natural numbers were used for counting purpose, hence they are also called the counting numbers. So 1, 2, 3, so on. The number 1 quantifies 1. The number 2 quantifies 2. Like this. So to quantify null value we use the number 0. The number 0 quantifies the nullity. Now, these numbers are not enough for our daily use, right? So these 1, 2, 3 will indicate quantities. We can quantify something. So if I say 30 students in the class, that means there are 30 by counting 30 students. So if there are no students, I will say 0 students. But these numbers are not enough for our calculations and are also daily purpose. So hence we introduce a new number system called the integers. So this integers number system includes again 0, 1, 2, 3. Along with these numbers, we introduce numbers called negative numbers. Those are -1, -2, -3, so this is how we represent the set of all integers. So this is called the integer number system. Integer number system. So how we can use this in daily life, right? So suppose if I have 10 rupees and if you want to purchase something of 5 rupees, so I have to give 5 rupees to the shopkeeper out of 10 rupees. So I subtract it. So the remaining amount with you is 5 rupees, right? Suppose I have 3 rupees, but I have to buy the same thing of rupees 5. So actually I have to give 5 rupees to the shopkeeper out of 3 rupees which I have. So what is this? 3 minus 5 is -2. So what does -2 indicates? Deficit. That means I have 2 rupees less with me to buy a 5 rupees thing. Right? So negative numbers are used in daily life to indicate deficit. So if there is any deficiency, we'll use negative numbers. Right? So then comes the rational number system. So and once again, the numbers 0, positive numbers and negative numbers. So these are not enough for our calculation purpose and also for daily usage. So hence, we extend the integer number system to the rational number system, and it is denoted by Q. So how we define the set of all rational numbers? So the rational number system. Rational number system. The rational number system consists of the numbers of the form P by Q. So fractions. All fractions will come under rational numbers. All the numbers of the form P by Q, where P and Q are integers. Where P and Q are any integers with Q is non-zero. So all the numbers of the form P by Q, where P and Q are integers with Q not equal to 0. So all these numbers will constitute rational numbers. For example, rational numbers 1 by 2, 1 by 4, 3 by 5, 7 by 9, like this. So numbers of this form will constitute the rational number system. So these rational numbers are also categorized or characterized by their decimal representation. Right? So these rational numbers are also characterized by their decimal representation. So if you represent any rational number in the decimal form, so this decimal number will be a terminating decimal or a recurring decimal. Terminating decimal means after the decimal point the digits gets terminated. Recurring decimal means after the decimal point the digits will repeat in some pattern. For example, if I take the fraction or the rational number 1 by 2, so its decimal representation is 0.5. So that is 0.5. So in this decimal representation, after the decimal point, the digits gets terminated. 5 is the last digit. So it is a terminating decimal. Likewise, if I consider 1 by 3. 1 by 3. So what is the decimal representation of 1 by 3? So to get the decimal representation of 1 by 3, we have to divide 1 by 3. So it is a smaller value, so I have to add a 0 by putting a decimal form. So 3 3s are 9. Once again, I got the remainder 1. So already have a decimal point, so I can add as many zeros I need in every step. So once again, 3 3s are 9. It goes on. It goes on. So it is a never-ending process. So the decimal representation of 1 by 3 is 0.3333. So it goes on. So it is a non-terminating decimal, but it is a recurring decimal because the digits after the decimal point repeat, and that digit is 3. In this way, if you represent any rational number in the decimal form, either it is a terminating decimal or it is a recurring decimal. Right? Now, so with this observation, now I can find some numbers, some fractions. For example, 22 by 7. So if I expose this in the decimal representation, so I want to divide 22 by 7. Right? 7, 3 side goes with 3. 7 3 is 21. So remainder is 1. Now 7 is bigger than 1. So I have to make this number bigger than 7. So I will add a point here. 7. So we get 0. 7 ones are 7. So the remainder is 3. So continue this process. You will get the decimal representation 3.142 and so on digits. So a non-recurring decimal representation I will get for 22 by 7. So this number will have non-terminating and non-recurring also. So it is non-terminating because this division process goes on non-ending. It is a non-ending process. So the digits after the decimal point will come flowing, and I also get different digits. So there is no repetition of digits after the decimal point. So it is a non-terminating and non-recurring decimal. So all those numbers will distinguish from rational numbers because rational numbers will have terminating or recurring decimal format, decimal form, and these like numbers like this will have non-terminating and non-recurring decimal form, and all such numbers will come under the number system irrational numbers. Irrational word is an opposite for rational numbers. All those numbers which are not rational numbers, not rational numbers means they will not have terminating decimal form or all recurring decimal form. So all those numbers will come under the number system called irrational number system. So it is denoted by I. So it has no standard notation. You can denote it by I, or we can denote it by Q star. Q star. So Q star is the irrational number system. Irrational number system. So this number system consists of all numbers which are not rational numbers by its decimal representation. By writing its decimal representation, we distinguish that number from rational number and we put it under the number system, the irrational number system. The next number system is the fifth one. Next is what we'll do is, so I'll combine both the rational numbers and the irrational numbers. I'll combine rational numbers and the irrational numbers. This is the set union representation. So I combine both the sets. Q is the set of all rational numbers and Q star is the set of all irrational numbers. So if I combine both the sets, I get a new set of numbers which is called the real numbers. So R is the set of all real numbers. Set of all real numbers, or we can call it as the real number system. The real number system. Right? So these are the well-known number systems which we deal with in the mathematics subject. Right? So on these numbers, so as they are sets, all these number systems as they are sets, we can define some operations on it. Right? We can define some operations. And we say that those are binary operations in mathematics. Right? Now, if I consider now I consider the biggest number system which we know till now, that is the set of all reals. Set of all reals. So on this set we define binary operations, right? So we define addition operation, we can define multiplication operation. So with these operations we can induce an algebraic structure on these number systems. We all know R, the set of all real numbers with respect to the binary operations, addition and multiplication. Usually we will denote multiplication by dot. So R along with two binary operations called addition and multiplication forms a field. Forms a field. You know what do you mean by a field? So field is an algebraic structure. It is an algebraic structure. So you know many algebraic structures. It starts from group, ring, field, vector spaces, like this. So among that, field is one, and R with respect to two binary operations. Addition, that is usual addition which we use. That is 2 plus 3 is 5. And usual multiplication. So the set of all real numbers with respect to usual addition and usual multiplication forms a field. Forms a field. Right? Now the question is the set of all real numbers is sufficient? Is the set of all real numbers is sufficient? Are we sufficient with the set of all real numbers? Don't we need extra numbers? Right? So to justify that statement, I consider a quadratic equation x square plus 1 equals 0. Consider the quadratic equation x square plus 1 equals 0. The standard form of any quadratic equation is ax square plus bx plus c equals 0 with the leading coefficient a is not 0. This is the standard form of a quadratic equation. And solutions for this quadratic equation are given by the formula x equals minus b plus or minus square root of b square minus 4ac divided by 2. So we know that any quadratic equation will have two solutions, and those two solutions are given by minus b plus square root of b square minus 4ac by 2a, and another one is minus b minus square root of b square minus 4ac by 2a. And in the standard 7 or 8 or 7 standard, we have discussed about nature of roots. Nature of roots of quadratic equation depends on the value of this one, b square minus 4ac. It is denoted by delta. It is denoted by capital delta, b square minus 4ac, and it is called the discriminant. It is called the discriminant. So based on the value of the discriminant, the nature of roots depend. We know that whenever the discriminant is non-negative, then only this quadratic equation will have roots in the real number system. In the real number system. Right? Whenever it is positive or equal to 0. Because this discriminant is inside the square root. If at all discriminant becomes negative, so we are unable to find square root of a negative number. Because, so what do you mean by square root? For example, what do you mean by square root of 4? So square root of 4 is a number whose square is 4. So it is a number whose square gives 4. And we know that 2 square is 4 and also minus 2 square is also 4. So if I square 2 or minus 2, I will get 4. So hence square root of 4 is plus or minus 2. Square root of any number is number whose square is the given number. Now, if the definition of square root, if I put a negative number inside a square root. Now, is there any number whose square is a negative number? Right? So suppose if I write a negative number inside square root, then I cannot define the square root because there is no number whose square is negative number. ಯಾವ number square ಮಾಡಿದ್ರು ಕೂಡ will not get a negative number. Hence, we cannot define square root of a negative number. Hence, we will not get roots. We will not get roots for the quadratic equation. Right? So this shows that the set of 4 real numbers are insufficient for our calculation. Because in particular, if I consider the quadratic equation x square plus 1 equals 0. Here a is 1 because coefficient of x square is 1, b is 0 here because there is no term with the variable x, and in case of c we have 1. So now if I calculate the discriminant b square minus 4ac, so it is 0 minus 4 into 1 into 1. It is minus 1. It is minus 1, which is negative. So in this formula, if I substitute all the values of a, b, and c, so what I get? X equals minus 0 plus or minus square root of minus 4 divided by 2 into 1 is 2. Right? Now, I don't know the value of this. I cannot define square root of minus 4. So, I will not get any number here. As a roots of x square plus 1 equals c. So that means there are no real numbers which can become roots of this quadratic equation. So what it shows, these real numbers are insufficient. They are not sufficient for our calculation purpose. Henceforth, we introduce a new number system. And what is the problem which we are facing here? So the problem here we are facing is we cannot define square root of a negative number, right? So this problem leads to the non-existence of roots for this quadratic equation. So to overcome this problem, what we will do is, we introduce a symbolic constant. Square root of minus 1. We introduce square root of minus of unity. So, and we denote it by I. We introduce a symbolic constant square root of minus 1 is a constant value square root of minus 1 and we name it as I. And this symbolic constant is called the imaginary unit. Imaginary unit. With the property, so if I square it on both sides, so I square is square root of minus 1 whole square, that is minus 1. So we introduce a symbolic constant square root of minus 1 and we denote it by small I, alphabet I, and we call it as the imaginary unit. And this symbolic constant has the property I square equals minus 1. Okay. So now, by introducing the symbolic constant, now we come to a new number system. And those numbers are called the complex numbers. And now we shall define those numbers. The numbers of the form a plus ib. The numbers of the form a plus ib where a and b are any real numbers. So the numbers of the form a plus ib are called the complex numbers. Right? So using the existing real numbers and new symbolic constant I, we generate new type of numbers which are of the form a plus ib. A plus ib. A and b are real numbers and ib is the symbolic constant square root of minus 1. And usually we denote these complex numbers by z. We use the small alphabet z to denote complex numbers. And in this complex number a plus ib, a is called the real part of the complex number z, and b is called the imaginary part of the complex number z. Right? For example, so if I take some example for complex numbers, so use any real numbers a and b and write them in this format. For if I take a is 2 and b is 3, combine 2 and 3 in this format. Then I get the complex number 2 plus I into 2 plus I into 3, or I can read it as 2 plus 3. It is an example for a complex number. And here we can vary a and b over the set of all real numbers. A and b can take any real number values. Now, writing all possible complex numbers. And if I collect all those numbers under a single set, then that set is called the set of all complex numbers, or we say it as the complex number system. That is the set of all complex numbers. The set of all complex numbers is called the complex number system. And it is denoted by denoted by script C. We denote the set of all complex numbers by C. And symbolically, or in the form of set, I can write the set of four complex numbers as. So, what is the set of four complex numbers? So, I have to collect all the complex numbers. I have to collect all the complex numbers under a single set. Then it will form the complex number system. So, how are the complex numbers? They are a plus I. They are of the form a plus I. So, I have to collect all the numbers of the form a plus I. Where what is the condition? A and B are real numbers. A and B are real numbers, and what is I? It is the symbolic constant minus 1, square root of minus 1. So this is the set representation. It is the set representation for the complex number system. So the complex number system is the set of all numbers of the form a plus I b, which are called complex numbers. Now, some observation. So, in the complex number a plus ib, consider any complex number z is equal to a plus ib. It is a general complex number. This complex number is said to be purely imaginary. Any complex number is said to be purely imaginary if the real part of that complex number, that is a, is equal to c. In any complex number, if the real part is equal to 0, then that complex number is called purely imaginary complex number. Similarly, any complex number is called real if the imaginary part is 0. Imaginary part is 0. For example, that is, if I put a is equal to 0, the real part is 0, and if I take b to be say 2, then it is, what is a plus ib? It is 0 plus I into 2, or I can write it as 2i. So it is of the form of a complex number, right? It is a complex number whose real part is 0. So it is called a purely imaginary complex number, right? Similarly, if I take a to be some 3, and if I put b is equal to 0, then what is the complex number a plus ib? So under the place a, I have to put 3 plus I into 0. And you know that 0 into any number is 0, because I is symbolic constant square root of minus 1. So 0 into anything is 0. So I will be dealing with 3. And you know that 3 is a real number. 3 is a real number. So in this way, you can observe that any real number can be expressed in the form 3 plus I into 0, which is a complex number, whose imaginary part is 0. Hence, that complex number is called real. So, by this observation, you can see that every real number is also a complex number. Because if you consider any real number, any general real number, consider an arbitrary real number. Suppose x is a real number, means I can express x as x plus I into z, because 0 and anything is 0, 0 plus x is again x. So now observe this, x is a real number, 0 is also a real number. So it is of the form a plus I into b, where a and b are real numbers. So it is the form of a complex number. So it is a complex number. So every real number is a complex number. Every real number is a complex number. And in the set of complex number, we have two types. So purely imaginary complex numbers and real complex numbers. So purely imaginary means the real part has to be 0. Real means the imaginary part has to be 0. Now in particular, consider the real number 0. Consider the real number 0. So I can write it as 0 plus I into 0. Right? 0 into I is 0. 0 plus 0 is 0. So basically 0 is a real number, and now I am writing that in the complex number form, right? 0 plus I into 0. It is a complex number. It is a complex number. So 0 is also a complex number with the form 0 plus I0. And now in this form, observe that the real part of this complex number is 0. If the real part of that complex number is 0, it is called purely imaginary. So it is purely imaginary. And now the imaginary part of this complex number is also 0. If the imaginary part is 0, it is called real. So it is real also. So thus I can conclude 0 is the only complex number. 0 is the only complex number which is simultaneously purely imaginary and real. It is both purely imaginary and real, and it is the only number with this property, because we cannot find no other complex number which is both purely imaginary and real. Right? So this is an important observation on the set of all complex numbers. And by this observation, I conclude this session.